Hello, my name is Nikos Katzouris. I work at the Institute of Informatics at the Democratic Research Center in Athens, and I will present joint work with Alexander Artikis on a statistical relational learning, online statistical relational learning framework on assets and programming with a focus on temporal domains. So I would like to start by saying a few things on the motivation behind this work, the application domain, which is complex event recognition. So event recognition systems accept as input so-called simple events, which may be, for example, sensor data, which are filtered through a set of complex event definitions or complex event patterns in order to recognize a set of complex events, which are defined as spatiotemporal combinations of the input events. So in this slide, as an example, I'm showing an application domain that we've worked on regarding human activity recognition. So on the input side, we may have logical representations of low-level activities, that is, activities that concern single individuals and other spatiotemporal knowledge, for example, coordinates in time of persons or direction of persons in time and stuff like that. And from this input, we want to recognize complex activities, that is, activities that involve more than one person. For example, two people that meet each other, like interacting or moving together or fighting and things like that. So the problem is one of temporal reasoning. So to account for that, we use an efficient implementation, efficient dialect of the event calculus. I'm just showing the very core, two simplified core actions of the formalism there, whose purpose is to formalize the common sense law of inertia. So when a complex event holds based on when it has been initiated or terminated in time. And given such a reasoning engine, then the set of event patterns is just a set of so-called domain-specific actions, that is, a set of rules that specify the conditions that initiate and terminate the complex events. So given complex event patterns, the reasoning engine and the data, the purpose is to recognize specific time points or even whole intervals where a complex event holds in time. The problem now is that these complex event patterns, they can be written by hand by domain experts, but this of course is error-prone and tedious. So ideally, we would like to have automated algorithms that learn these patterns from data. So in our learning setting, the input consists of streams of simple events annotated with complex event instances. So these things over there serve as the supervision, the annotation, and the goal is given a version of the event calculus as background knowledge to learn domain-specific actions. So the requirements for that is that we need to be able to handle noise and uncertainty. We can find tools for that in the field of statistical relational learning, basically combining logical representations with probability. And we also need to have algorithms which scale well to big data volumes or even open-ended data streams. And in order to account for that, we choose online algorithms, single-pass algorithms, which means that the data are presented to the learner in small data batches, and the learner has the opportunity to process each data batch only once, extract the necessary information for learning, and then the batch is discarded. That's single pass. So just a reminder, in statistical relational learning, there are two core learning tasks: learning the structure of rules, and we have tools from that from inductive logic programming, and learning the weights of rules, which are typically realized via gradient-based techniques. So in this work, we focus on instantiating a statistical relational framework on associative programming. Why we want to do that? Because we have non-monotonic semantics out of the box, and we need that in order to reason with time and change and events. We also have sophisticated solvers off the shelf, which provide efficient tools for grounding, solving uncertainty modeling and optimization, for example, Klingo. And as it turns out, structure and weight tasks, structure and weight learning tasks which are involved in statistical relational learning can be encoded in ASP, encoded and solved as optimization tasks in ASP. How we do that? We use a well-known probabilistic ASP framework put forth by Lee and Yang in this paper over here. It is very similar to Markov logic networks. Basically, we have real-valued weights attached to rules, and these weights define a probability distribution over answer sets. In contrast, for example, to Markov logic, where we have weights defining probability distributions over possible worlds. So, given this probability distribution over answer sets, the main task that we concern ourselves with is MAP inference. MAP over here stands for maximum a posteriori. Arguably, it's the workhorse of statistical relational learning. Most approaches utilize this sort of inference. The task here is to find a most probable answer set given the probability distribution defined by the weights. This turns out to be a weighted max-out problem, which amounts to finding an answer set that maximizes the sum of weights of the satisfied rules. And the important thing is that, as can be seen by this kind of pseudocode here, this can be easily encoded and solved directly as an optimization task in ASP using constructs like choice rules and weak constraints. So we can realize map inference directly in an answer set solver. So when we receive a data batch, a small batch of data, then we perform map inference to acquire a map inferred state, and we compare that to the true state, to the supervision, which we receive shortly after the prediction. And based on the comparison, based on the mistakes that our current theory makes, we want to update the weights and the structure. Concerning the weights, in this approach, we used a weight update based on the Adagrad algorithm. This is an adaptive version of online gradient descent. It's adaptive in the sense that the learning rates depends on the past performance of its rule. So the weight of its rule, of course, it's updated individually. We have a loss function whose gradient corresponds to a vector, and its coordinate in this vector corresponds to a weight update for its rule. Past mistakes are taken into account for its rule, which gives this sort of adaptive flavor to the algorithm. And the other important thing is that we have a regularization, L1 regularization rate over here, whose purpose is to eventually push the weights of irrelevant rules to zero. So in order to learn some sort of sparse theories where only useful rules are kept with non-zero weights. Regarding structural learning, we have structural learning concerns two main tasks. The first one is to construct new rules from mistakes. The second one is to revise rules over time. I will talk about that in a second. Concerning the first one, we have as input the current data batch, the existing theory of weighted rules, ASP theory, and our background knowledge, which are passed in the map inference module, where we acquire an inferred state, which we compare to the supervision, the true state. We extract the mistakes, and then we encode these mistakes into bottom rules. Bottom rules are most specific rules in a particular language, which each of these rules has the potential to correct these mistakes. Of course, now these rules are too specific to be of any use for prediction. So what we need to do is to generalize from these rules in order to approximate, in a sense, the true state. So the bottom rules are probably transformed into a diffusible form along with the existing weighted rules and the background knowledge, and a search in the space of theories that theta subsumes this thing over here takes place in order to learn new rules. We use techniques from non-monotonic ILP for this task. And the important thing is that the search in the space of theories over here is part of the same optimization process as the one that we use in order to perform map inference with the rules. So in a sense, we only learn new rules only insofar as they're really useful given the past theory, the theory that we already have. So this is an important asset of this advantage of this approach. Now, when we learn rules over time and new data arrive, we found ourselves, we found these rules frequently to be of low quality, and we need to revise them. Revision in our framework is about specializing rules. So what we do is we instantiate a search, top-down search in a theta subsumption lattice, which is bounded from below by a bottom rule. This bottom rule is generated over here, and its new rule, which is generated in this step, is associated with the bottom rule, and the bottom rule serves as a pool to draw literals from to perform specializations. So we search in a top-down fashion in a subsumption lattice here, and we use a sort of online hill climbing using hefting tests. This is a very simple statistical tool that allows us to select a specialization at each level of this subsumption lattice with high probability among its peers. So at each step, we add conditions to the rule and we continue doing so as long as the performance of a single individual rule is improved. So putting it all together, this box over here represents the core algorithm. WOLED stands for Online Learning of Weighted Event Definitions. ASP, I think it explains itself. So as far as data are concerned, we have the data are presented, like I said, in mini batches, training interpretations, sets of true ground atoms, some of which are of special significance. For example, these things over here represent the annotation, the supervision. We have the background knowledge, we have some syntactic language bias in order to facilitate the learning task, and a continuously revised theory, which is tested upon the data and revised if necessary. The first step is to perform a probabilistic inference, then theory expansion step, which amounts to this step over here. We have hefting tests and rule expansion. If we need to specialize the rules, we update the weights for old and new rules, and the whole loop continues for as long as we receive. So in this wraps it up concerning the description of the main framework. Now, a few words on the experimental evaluation. We used 3 different datasets from 3 different application domains for complex event recognition. The first one is about human activity recognition. I already talked about that in the beginning. We have 28 videos transcribed in logical form. These videos are annotated with various activities of complex activities of more than 1 persons. We used 2 target events here, 2 persons moving together or meeting each other. These are the events for which, these are the events we want to learn definitions for. Then we have maritime surveillance. This dataset consists of AIS signals of vessels sailing around the area of Brest in France. We have 6 months worth of data, and the target event here was to learn definitions for suspicious vessel rendezvous. This means this holds when, for example, 2 vessels meet in the open sea, potentially being involved in suspicious activities. And these are things that domain experts would like to be aware of. The third application is about vehicle fleet management. It's about commercial vehicle fleets. The dataset consists of GPS signals from sensors installed on such commercial vehicles. We have 1 month worth of data. The target event here was dangerous driving, which holds when, for example, various conditions involving abrupt acceleration, sharp cornering, combined with weather conditions and static information like schools, habited areas, and stuff like that, all this information combined together. So we want to learn rules to detect when vehicles drive in a dangerous fashion. In our first experiment, the purpose was to compare the scalability of MAP inference in the ASP implementation of the algorithm versus an implementation based on Markov logic networks. So this one over here is the algorithm I've been talking about. It completely relies on Klingo, whereas the MLN implementation, it is based on a custom library called LOMRF for Markov logic, and it uses an open source integer linear programming library. This is used exclusively for performing MAP inference. The experimental setting is that we used a fixed event pattern set. We didn't mess with the structure at all, but we performed MAP inference only for weight learning, while varying the batch sizes at the input. And as you can understand, while as the batch sizes vary, so does the size of the ground program that the solvers need to deal with. So the x-axis in these graphs represents the average size of the ground program, while the y-axis represents the accumulated grounding and solving time in seconds for the 2 solvers. And,
because 1 minute left, okay.
Yes, and as we can see from the graphs, the implementation based on ASP and Klingo takes almost constant time, while the MLN implementation grows nearly exponentially. This is a first advantage of using ASP in this approach. In our second experiment, what we want to do is to assess the learning performance. So we evaluated the ASP and the MLN implementation to OLED, which is just, it learns in an online fashion crisp rules, a handcrafted set of rules, and handcrafted with weight learning. We measure the prequential loss, which is the online loss, a measure of how well an online learner incorporates new information. And as can be seen from the results, WOLED ASP beats its peers in all complex events. F1 score is about generalization performance. So this involves a cross-validation on evaluating a model on unseen data. And again, we have the best performance here. Both these results can be attributed to the fact that weight learning and structured learning are tightly coupled in our new implementation, thanks to the ASP optimization tools. This column over here, it concerns only the MLN implementation. This is important because we need to do an extra computational step to compute predicate theory completion in order to have the non-monotonic semantics in MLN. And in training time, we see that the ASP implementation is one of the best, has one of the best performances. Okay, so to summarize, we have presented an online structure and weight learner, which is implemented entirely in ASP. We have results that show that it is significantly more efficient and simpler to use than the MLN implementation. The code and the datasets are freely available. As future work, we are looking into things related to concept drift and scaling things up even further using distributed and parallel learning. So thank you for your attention.